All right, guys. Today we're going to look at how atoms form ions and then how they form compounds. You may recall from a previous lesson, we said that metals on the far left tend to react really well with group 17 nonmetals. And I'm going to show you today, hopefully, why that is. So, compounds to define a molecule is two or more atoms of the same or different elements that are chemically joined together in some sort of unit. And a chemical formula is a notation that indicates the type and number of atoms in a pure substance. So if there's no subscript, we'll just look at these ones: CO, CO2, CH4, H2O. If there's no subscript, it means there's one. So CO has one carbon atom and one oxygen atom. CO2 has one carbon atom and two oxygen atoms. So the subscript that tells you the number of those atoms comes after the element. CH4 has one carbon and four hydrogen, and H2O has two hydrogen and one oxygen. All right, that's how you count the atoms that are in these types of chemical formulas. Now, some elements just bond with themselves naturally. A molecule consisting of an atom of atoms of the same element, and there's 7 naturally occurring ones called diatomic elements. Like, you never find hydrogen just by itself; it's always H2 gas. Nitrogen's always N2, O2, F2, Cl2, Br2, and I2. Anyways, that's something that occurs. Don't worry too much about this diagram. We're not going to get into that sort of covalent bonding this year. That's a grade 10 topic, but that's what's happening there. There's 2 types of compounds: molecular compounds, and those are compounds that have 2 or more different elements. And the key here is that these are always nonmetals. 2 or more different, let's say, nonmetals. Let's actually change that up. The types of bonding they undergo involves sharing of electrons, and they're called covalent bonds. H2O, CO2, C12H22, O11, or CH4 are all examples of molecular compounds because they are all nonmetals bonded together. Other than what you see here, that's all we're going to deal with for molecular compounds. Most of this lesson is going to be based on ionic compounds. And ionic compounds consist of 2 or more different elements. The key for an ionic compound is it has to be a metal and a non-metal. For example, NaCl. The metal is always written first, followed by the non-metal. So there's a metal, and this is your non-metal. That's an ionic compound, all right? But what is an ion? Atoms tend to form stable ions by losing or gaining electrons. And this next part's very important. Atoms are most stable when they have either 2 or 8 electrons in their outer orbits. In other words, their outer orbits are full. For example, sodium here, it's got 11 protons, 11 neutrons, and then it's also going to have 11 electrons. So they're placed properly: 2 in the first orbit, 8 in the second, and then 1 in the last. All right. So in the outer orbit, there is 1 electron. So the way that sodium makes a stable ion is it just gets rid of that outer electron. So now it only has 10 electrons instead of 11, which you can see down here in the next diagram: 10 negatives and 11 positives. The 11 positives come from the proton. So sodium loses that electron and therefore has a net charge of +1. Positive ions are called cations. Let's look and do the same thing with chlorine. Now, chlorine has 17 electrons normally, so 2 in the first orbit, 8 in the second orbit, 7 in the third orbit. So it's missing one in its outer orbit. So what it likes to do to form a stable ion is gain an electron in its outer orbit. And then instead of 17 electrons, it has 18 electrons because we've added one. So chlorine gains an electron, and therefore, and electrons are negative, so it has a -1 charge. Negative ions are called anions instead of cations. So that's how atoms form stable ions. I mean, we can use another example, oxygen. And I'm just going to back out of this and find. Well, I don't need to do that. We're going to keep these annotations for a minute, and I think I have your periodic table up someplace. Here we go. So you find oxygen on the periodic table, just like drawing the Bohr-Rutherford diagrams, we find it's element number 8. I'm not even going to worry about the neutrons because they don't even come to play here. But let's just go back into this and see what we can do with oxygen. So it's 8. So in the first orbit, obviously it's got 2 electrons. And in the second orbit, to make 8 total electrons, it's got 1, 2, 3, 4, 5, and 6. Just going to change my pen color here for a second to blue. See what that looks like. That's all right. So hopefully you guys can see that. Two electrons in the first orbit and 2, 4, 6 in the second orbit. So what oxygen does to become stable is it's going to gain 2 electrons. One to go right there, one to go right there. What's its charge going to be if it gains 2 electrons? Instead of 8, now it has 10 negative electrons. Its charge, of course, will be -2 because it gained 2 negatives. Would it be a cation or an anion? It'd be an anion because anions are negative ions. So we haven't even talked about bonding yet or ionic compounds, just what do atoms do to form stable ions? And an ion is just when it has a different number of protons and electrons. The sodium now has 10 and 11, the chlorine now has 18 and 17, and oxygen now has 10 and 8, as opposed to its normal neutral state where the protons and the electrons are equal. These aren't regular atoms, these are ions. Let's look at magnesium. Magnesium has which one is magnesium? I think it's number 12, which puts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12. So the outer orbit of magnesium has 2 electrons. Now, I mean, if you just think of it logically, is magnesium going to gain 6 electrons to stabilize its outer orbit, or will it lose 2? And the answer is it will lose those 2 outer electrons. Now, you may even come into this other word. Outer electrons are sometimes or often referred to as valence electrons. All right, so it loses 2. If it loses 2 negatives, it's going to have a +2 charge because now it has more protons than electrons. Remember, it's got 12 protons in the nucleus. Again, I'm ignoring the neutrons here because they really have nothing to do with how these things form stable ions. As a general rule, if it doesn't say so here, well, we'll do chlorine first and then I'll talk about it. So chlorine's a non-metal. Have we dealt with chlorine yet? Yeah, it was on one of the slides, but I'll just do it again. So 2 electrons in the first orbit, 8 in the second. I like pairing them up like this because it helps me keep track of what's here. 2 in the first orbit, 8 in the second, 8 in the third. Or actually, normally it just has 7 in the third, I should say. 1, 2, 3, 4, 5, 6, 7. All right. Because it is element number 17. Now, what it'll do to become stable is what's it got? It's missing an electron in its outer shell to fill up that orbit, to fill up that energy level. So it gains one electron, giving it a charge of -1, which makes it an anion. Anion. Need some spelling practice there. Anyways, as a general rule, when you gain electrons, you get a negative ion, which is an anion. Positive ions are the cations. Nonmetals tend to gain electrons and form, well, that's actually correct. Nonmetals gain electrons and form anions, and then metals lose electrons and form cations. There we go. I got a little tongue-tied there for a second. So that's a good rule. So anything you see on the left side of the periodic table is going to do this. No, anything on the left side of the periodic table is going to do this, and anything on the right side of the periodic table is going to do this. All right, gain electrons and form negative ions. All right, so I'm actually going to change this one up a bit just to make it a little simpler for myself. We've already done the ion for chlorine, so let's just make sure we do a different one we haven't done yet. Let's do lithium and chlorine. So lithium is element number 3. So it's got 3 protons, and I'm going to make my 3 electrons. 1, 2, 3. Before I even draw it in, you should be okay now to think about it and think, okay, so what does lithium do to form a stable ion? Anybody? All right, I'll do it. It's going to lose 1 electron. It wants to lose that outer electron to stabilize, because then its outer orbit will be full, because remember that first orbit does hold just 2 electrons. And I'm going to react that with, let's say fluorine. Fluorine is element number 9, so it's got 9 protons, and I'm going to make 9 electrons. 1, 2 in the first orbit, and then 7 in the second orbit. 1, 2, 3, 4, 5, 6, and 7. So what does fluorine want to do to make a stable ion? It wants to gain 1 electron. So lithium wants to lose 1 electron, and fluorine would like to gain 1 electron. So what do you think will happen in nature, in real life, if you mix these 2 elements together? One of them desperately wants to lose 1 electron to stabilize. One of them wants to gain 1 electron to stabilize. So I'm sure many of you have guessed it by now. The lithium will donate that 1 electron to the fluorine, giving fluorine a -1 charge and giving the lithium a +1 charge. And that makes the compound lithium fluoride. Now, I haven't told you yet, well, why do these 2 things stick together? They stick together because of the law of electrostatic charges. Lithium, all the lithiums here are going to have a +1 charge, and fluorine's always going to have a -1 charge. So it's going to make LiF. Li is the symbol for lithium, and F is the symbol for fluorine. The reason they stick together so well is because the lithium's positively charged and the fluorine's going to be negatively charged, and then they're going to stick together really, really, really well. Lithium's in group 1 and fluorine is in group 17. All those elements in group 1, that alkali metals, they like to lose 1 electron to become stable, because they all have 1 electron in their outer energy level, their outer orbit. All of the elements in group 17 with fluorine, they all want to gain 1 electron because they all have 7 electrons in their outer orbit. And that's what makes group 1 and group 17 really good reaction partners, because it's very easy to stick them together like that. So the last thing to just mention quickly is how to name it. So the metal keeps its name. It's just lithium. And then the non-metal gets an IDE ending, so it's fluoride. Lithium fluoride, calcium oxide, sodium chloride is table salt, right? So that's the way that goes. I can't remember what's on this last slide here. Oh, we got ourselves a little animation for NaCl, sodium chloride, table salt. Look how the sodium donates that one electron. Then it's the same thing. Sodium's going to have a positive one charge and chlorine's going to have a negative one charge, and they'll stick together. Very, very difficult to break them apart, as a matter of fact. So let's get out of this PowerPoint now that we've completed that, and just have a look at what I want you to do for the rest of the day. Do I need a periodic table attached here? You guys should have your textbook, so you should be fine, but maybe I will attach one just in case. But this really does bring us to the end of our chapter here. So I don't have any official work to go with this thing on ions. What I want you to do, though, is go to the Chapter 6 self-quiz, which I've attached to today's lesson. And it's in the textbook, too. It's on page 250 and 251. And I just want you to go through it and kind of test yourself. I'm not going to make the chapter assessment any more difficult than this, and the chapter assessment will be on Wednesday. And it's not a real test; it's a chapter assessment, guys. So send me the emails if you get stuck on anything. Like, the idea is that I can help you through it, and you'll get perfect on it. Email me when you get stuck. I think that's all I have to say about that, guys. Go through this video lesson again if you need to, and pause it in certain spots, and then work on that Chapter 6 self-quiz. And, I'm going to fashion something out of that for a chapter assessment later in the week, okay? I think that's all for now, guys. Chemistry's been a blast. Good luck.